Mhm. Did he come and want to see this as well?
Oh,
That's
I
right.
just saw some people up there.
Maybe Nancy called Sean to have him come down. I mean, Sean.
So I didn't realize I'm sorry.
No, no.
It's already.
I said before, you know, so it's like that Sean told me. Sorry. She was
Oh, okay.
like, it's fine. She'll settle it down.
But now it's close to the time.
Yeah, exactly.
So I just.
Thanks. Thank you. Mhm. I'm just gonna check. Hello, welcome. Come on in. Okay, welcome to the Royal Astronomical Society. My name is Lucinda Offer, and I am one of the education and outreach officers here at our organization. This is a public talk, one of 8 that we have every year. This is the first one of the season, and I'm really excited to begin and to welcome you into Burlington House. So I did all the public talks over COVID, which all the online talks, all our online content, and it's really nice to be back in the building and to welcome you here. And it's a beautiful sunny day outside, blue sky, a little chilly. So hopefully, and I think we have the heaters on, but hopefully the room will warm up a bit for you today. So today I'd like to welcome to you our first speaker for public talks, Dr. Idis van Zelst. The title of her talk is Venus, Cloudy with the Chance of Earthquakes. She's a postdoctoral research fellow at the German Aerospace Center and the Technical University of Berlin in Germany. And she studies the geophysics of Earth and Venus and is particularly fascinated by the geodynamics and seismology of those planets. She has a BSc and an MSc in Earth Sciences and Geophysics from Utrecht University in the Netherlands, a PhD from ETH Zurich in Switzerland, in 2020 researching tsunami-genic earthquakes, a postdoctoral research associate at the University of Leeds. So she's been local here in the UK as well, and we hope to welcome you back someday. And she also develops educational games, her current one called Quartetnary. And the geological time, it's about the geological time scale. And she does science videos, women in science, and she likes to combine science and theater. If you ever get a chance to look her up on YouTube, she's got lots of really informative YouTube videos about science and being a geophysicist, and especially a PhD geophysicist. So if you're ever interested in sharing that with a young person who wants to become a geophysicist, I highly recommend it. But please welcome Dr. van Zelst.
Right, thank you very much for having me. This is very exciting. Let's see if this works. Right, so welcome to Venus, cloudy with a chance of earthquakes. And I basically want to show you a little bit about how Venus has been explored over the ages and some questions that people have been asking over the past few years. Some of them have answers, some of them are still very much in the process of being discovered, and hopefully show you that Venus really is a very interesting planet to keep your mind on for the next few years, with lots of new discoveries on the horizon. So let's see if this works. Yes, it does. Great. So this is Venus. If you look through your telescope or just up in the night sky, this is what you see. And it's a very striking planet because it's the brightest star planet in the sky that you can see. And people, for a very long time have recognized that Venus is such a bright light in the sky. And therefore, when they saw this star or this planet, the ancient Romans already called her Venus, after the goddess of love and beauty, because it was the most beautiful star in the sky. Then, we'll take a bit of a leap in terms of exploration of Venus. And one particular story I want to tell you is in the 19th century, people were trying to observe the surface of Venus, because just like Mars and the Earth, you can learn a lot about a planet by looking at its surface. We now know that Venus is covered in clouds, so these are just clouds and it's very difficult to see actual surface. But people didn't know that in the 19th century, so they tried very hard. And one particular person who really tried very hard was Percival Lowell. And he made the first surface topography map of Venus that you can see here. You can see all these weird kind of spokes and things. So, there is, for the first time, a surface map of Venus, or so he thought. He was very excited by it, but again, it's covered in clouds, so we literally can't see the surface from the Earth. So what turned out to be the case was that this Percival Lowell was so enthusiastic, and he wanted to observe the surface of Venus so badly that he had made this kind of instrument, this telescope, that was so so big, and he was looking at it at such a weird angle, at such a bright target, because Venus is very bright, that he accidentally made an optical instrument by which he viewed his own eye. So these are not spokes on the surface of Venus. These are the blood vessels in Percival Lowell's eye. So he tried, he gave it the best shot, but yeah, we really can't see the surface very easily from the Earth. So we'll take another leap and we'll go to the early 20th century. And at that time, people thought, well, okay, so there's clouds. What are clouds made of on the Earth? Water vapor. So there's a lot of water on Venus, right? That makes sense. It's closer to the sun, so it should be hotter there. So, where is it very humid and very watery? Rainforests, swamps. That's what Venus is gotta look like. It's a planet covered in oceans and swamps. And they also had a theory at that time about the origin of the solar system. We now know that that is wrong, but they thought that the further away a planet is from the sun, the older it is. So it was kind of flung out earlier and therefore had traveled further away. That was the idea. This is not true, but it kind of makes sense why they thought that way. So by that logic, Venus, because it's closer to the sun than the Earth, would be younger than the Earth, and therefore would maybe resemble the Earth a few million years ago. So that was the reigning idea of what Venus was like in the early 20th century. And of course, science fiction writers went ahead with it. And the consensus was there must be dinosaurs in rainforests on Venus. That's it. So you had lots of books, The Planet of Peril, The Port of Peril, The Oceans of Venus, Half-Breeds on Venus. As long as, there were dinosaurs and some rainforests, that was the idea. Which of course makes it a really exciting planet. I mean, who wouldn't want to go to a planet and explore it when you have the opportunity to find dinosaurs, right? So people were really into Venus. And then a few years later, there was the Second World War, and then it gradually turned into the Cold War between the US and the Soviet Union. And by that, we also got the space race. And of course, the moon narrative is very well known by the general public because the Americans were the first people to put a person on the moon. Well done. But there is also a Venus narrative, and the Russians kind of won that. So I want to kind of touch upon that, because the Russians had the Venera program to Venus, and that basically consisted of more or less the same mission, the same spacecraft, and launch it every other 6 months to Venus in the hopes of actually getting there, trying, if for some reason the mission crashed, which happened often, make minor improvements and just throw as much against the wall and see what sticks. I mean, that works. So they tried that and they started launching a lot of missions to Venus. Funnily enough, the US, the Americans, in 1962 with Mariner 2 were the first to actually do a flyby of Venus. So they flew past Venus and they used radiometry, and they realized that the surface of Venus is hot, and not just hot, like nice outside hot, but really hot. They measured it to be about 300 degrees Celsius, realizing, maybe this is not the environment where you can have dinosaurs or life as we know it if it's that hot. So they were kind of, intrigued, like what is happening? But yeah, people were still interested. And the Russians just kept going with their Venera missions. So at some point, Venera 8, they were successful, and they successfully landed on another planet. By successful, it means that it didn't crash. But it actually stayed alive, did a few measurements, but again, it realized Venus is really hot. It turns out that the surface temperature was 464 degrees Celsius, which kind of tends to melt your spacecraft. So it landed successfully and it stayed alive successfully for about 2 hours before everything melted and they couldn't reach it anymore. But yeah, this was the first successful landing on another planet. So that's a major achievement in the space race, right? And they had other achievements as well, the Soviets. Venera 9, a couple of years later, had the first images from the surface of another planet. And this is the first image of the surface of another planet, Venus. You can see lots of rocks, a bit of sand. Interesting, very intriguing. Then in 1978, the US had Pioneer Venus, which was mostly focused on the atmosphere of Venus. And then the Russians continued with lots of Venera missions, and they had another success with Venera 13, which had the first sound recordings from another planet and the first in color picture of another planet, which was this. And therefore you can see the artist impression of the surface, kind of yellowish. Yeah, and again, lots of rocks, interesting. Then in 1989, the US had another mission, Magellan, and Magellan had as a goal to map Venus, to finally look below the clouds and see what the surface looked like. Are there any structures that we recognize from Earth? What is happening on the surface? You know, it's been a long time, you want to see what's down there. And that ensured that for the first time, we could see what the surface of Venus was like. And this is what it is like. From radar measurements, I believe. And there are lots of interesting things happening that we will get into later in the talk. All right. Then in 2005, there was the next mission. As you can see, quite a big gap. People were very into Venus in the 70s, 80s, and then it kind of stopped. And the reasons for that were more or less twofold. At the end of the 1980s, early 90s, of course, the Soviet Union collapsed. And they had really been the nation driving Venus exploration. And therefore, people always had the idea, oh, it's kind of the Russian planet. You know, they had all these firsts on Venus. Let's not burn our fingers on that. Let's let them have it. And, you know, with the collapse of the Soviet Union, they obviously had other things to think about. They didn't want to spend lots of time throwing missions to Venus. So they stopped doing that, and they also lost that technology over the years because people retired and left science, etc. On the other hand, partly because people were thinking Venus is the Russian planet, but also because they realized it's very hot. There are no dinosaurs. You know, it wasn't that exciting anymore, the planet, because it was kind of dead. What could possibly live there? And at the same time, they realized maybe Mars, which is unexplored, is much more exciting. There might be water there. It's at least not that hot. Actually, it's very cold. So maybe there's some microbes. So they totally shifted their focus towards Mars. And all the space agencies started looking at Mars, and Venus was forgotten. So it took a really long time before we got another mission to Venus in 2005, which was Venus Express by the European Space Agency. And funnily enough, they didn't even mean to go to Venus. It's just that they wanted to go to Mars like everybody else, and they made Mars Express. But for contingency reasons, they made two, just in case the first one crashed. But the first one was successful, so they had this leftover Mars Express, and they asked the scientific community, does anyone have any ideas? Is there anyone who wants to do something with it? And then the Venus community was like, yes, please. It's been a really long time since you've been to Venus. Please send it to Venus. And they did. And they actually got a lot of nice results from that. So that was our one highlight in recent years. And then in 2010, we had Akatsuki from the Japanese Space Agency. And there were also some troubles, but eventually it actually arrived at Venus. But as you can see, you know, in the past, few years, few decades, 30 years or so, people were not that into Venus because it's boring, it's dead, there's nothing left to discover. Luckily, the thinking has changed, and I will tell you about what people think nowadays. But I just want to let you know that Venus, as we know it now, is going into, luckily, a new decade of Venus science. People have realized that Venus actually is really cool, and multiple space agencies are actually sending missions there. So if all goes well, obviously, because this is a very tricky business, in 2024, the Indian Space Agency will send a mission. China is working on a space mission to be launched in 2026. Then NASA is going to send Da Vinci Plus in 2028, which is a very interesting mission in that they send a capsule that with lots of instruments on board, and they throw it into the atmosphere, and then it crashes on the surface. But the idea is that it stays alive throughout its descent through the atmosphere. So they get 59 minutes of very exciting science while it drops through the surface, and you get a profile through the atmosphere and learn a lot about Venus that way. Then there is Veritas, another NASA mission, probably to be launched in 2028, 2030. There's a bit of funding problems because NASA is prioritizing Mars once again with Mars sample return. So we'll see when it actually launches, but Veritas has the aim to get much higher resolution topography data to say something more about the structures we see. And then the European Space Agency also has a mission which is to be launched in 2032, which is Envision, which will also look at tectonics and volcanism. All right, so let's talk about some Venus facts and what we know at the moment. As I said, it's very hot. It's hot enough to melt lead. There's also a very large surface pressure because there are so many clouds. It's a very thick cloud layer. So the surface pressure actually feels like you're standing at the bottom of the ocean on Earth. There's just so many clouds on top of you. Then the clouds are made up mostly, well, the atmosphere is made up mostly of carbon dioxide, when the clouds are made of sulfuric acid. So it really is not that nice of a place to go to. I'll concede on that. It has a very geologically young surface. People know this from crater counting. As if you look at the moon, you will see that there's lots of craters, and that means that there has been no plate tectonics that kind of renewed the surface. But on Earth, for example, you don't see a lot of craters because we have plate tectonics, and we get rid of the craters over time. On Venus, it's kind of in between. There's less than 1,000 craters, so not really that many, and it's more or less uniform across the surface. So that leads people to believe that it has a more or less uniform surface age of about 500 million years, depending on who you ask, maybe 100, maybe 1,000 million years, but geologically young in any case, which obviously begs the question, why? What happened 500 million years ago? Why is it so young? Does it mean Venus is still kind of active? What's the deal with that? So that's an interesting kind of question people struggle with Venus. Then it has a low backward spin rate, so planets spin, and Venus actually spins upside down or backwards, depending on how you want to call it. And it also means that a Venus day is longer than a Venus year because it spins so slowly around its own axis. It actually makes a circle around the sun more quickly than spinning its own axis. So that's interesting as well. There is no magnetic field that we know of. Of course, on Earth, we have a magnetic field and it protects us from lots of radioactive material from the sun. But Venus doesn't seem to have a magnetic field, or at least we've never measured it. Maybe it's so low that we haven't been able to measure it yet, but so far, nope. And then we don't know much about its interior either. So on Earth, we know there is a crust, a mantle, a core. We kind of know the same thing for Mars and Mercury, but on Venus, there are very large uncertainties and very large error bars, and we don't really know whether it has a core, what the size is it liquid or solid or both? So lots of things that we don't know, which is interesting because it makes it a prime target to study, right? Then lastly, something we do know is that it's a volcanic world. So in a recent paper published earlier this year, a colleague found 80,000 volcanoes on Venus, which is massive. That's a lot of volcanoes. And here there is a little map of Venus, and in red you can see all the volcanic units, which on Earth would be the oceanic crust, so the oceans, those are all volcanic. And here you see it's basically most of the planet, and all the triangles are volcanoes. And this is from a few years ago, so this is not even including all 80,000. And as you can see, lots of volcanoes. So if there are so many volcanoes, the question that kind of pops into your mind is Venus volcanically active at the moment? And we can have a look at some evidence for that. So the first thing is emissivity and topography. In the bottom figure here, you see the emissivity, which means kind of how bright something is. And if something is more bright, it means that it is not weathered. So it's really fresh rock, fresh lava, if you will. And as you can see, there are lots of bright spots, and these were observed by Venus Express. So that means that these areas are geologically young or unweathered. The question then is, what does that mean? And well, it again depends on who you talk to. So some people think that the weathering process of rocks takes a few million years. So maybe these recent bright spots are 2 million years old. So is it volcanically active on a geological timescale? Yes, but it's not like there was a volcanic eruption yesterday. Other people think that no, the weathering process of rocks is a really fast process, especially on Venus, because it has different conditions. And you can weather a rock within 30 years. So the fact that you see these bright spots means that these bright spots are new rock, fresh lava, less than 30 years old, which does mean that it's very active on the present time scale. So that's interesting. Depending on who you talk to, this could be, an indication, some piece of evidence for volcanic activity on Venus. But there is more. Over the course of many decades, there have been measurements of sulfur dioxide in the atmosphere, in this case, plotted specifically at 70 kilometers height. And first there was Pioneer Venus, and that mission measured the amount of sulfur dioxide. And as you can see, it starts high and then it kind of tapers off a bit. There is some variability. Okay, cool. And then there was a bit of a gap when there were no missions, but okay. And in the end, we got Venus Express in 2005 to 2010. And again, we see variability. It starts high, it kind of tapers off. There are some uncertainties. Main point being, it's not stationary. And that is odd because sulfur dioxide is a very reactive gas in the atmosphere. So it tends to react with other species to make something else. So you don't expect sulfur dioxide to stay in the atmosphere for very long. But it is there and in various quantities. Interesting. Another interesting fact that I should tell you is that on Earth, the cause of sulfur dioxide in the atmosphere is volcanism, active volcanism. So you would say, maybe the presence of sulfur dioxide in the atmosphere and its fluctuations is evidence for current volcanic activity on Venus. Could be. Lastly, a very recent piece of evidence by a paper published earlier this year is the paper from Herrick and Hensley, who looked at radar images. And I'm not very good at interpreting radar images, but they showed that if you look at the data from Magellan, who mapped the same region with a few months in between, and if nothing happens and the surface is stationary and nothing is active, then you would expect to see the same thing, right? That makes sense. But they saw that actually things changed. And so this is a before picture A and an after picture B, and they interpreted as the changes that we see could be a new lava flow. And they did some modeling studies to show, well, there is no real other explanation that could be there. So maybe Magellan actually saw an active lava, like a new lava flow, an active eruption. So another piece of evidence. So let's tentatively say, for the purposes of this talk, yes, Venus is currently volcanically active. Then, of course, that opens up a lot of other questions, namely, how often do you get these volcanic eruptions, and can we measure them with a bit more certainty? And people, again, have looked into this. And in order to figure out how often you would expect volcanic activity on Venus, people looked at the Earth, because we know how often roughly we have volcanic eruptions on Earth. And Venus is only slightly smaller than Earth. And yes, maybe it has very different tectonics, but as a first try, we can look at the Earth and try to scale it to Venus and see how many volcanic eruptions you could have then. So last year, two colleagues, Björn and Krishnamurti, looked at the databases of volcanoes on Earth, and they then sorted them by tectonic setting and looked at how often you can have a volcanic eruption if you scale it to Venus. And they looked at a 60-day time window to see how many volcanic eruptions you could have in a 60-day time window, because a balloon that is one of the mission proposals that could fly through the that could fly in the atmosphere could potentially stay alive for about 60 days before it kind of doesn't work anymore. So, you know, if you have a balloon that could measure whether or not there's volcanic activity in a 60-day time window, how many volcanic eruptions would you get? And the answer they came up with was 20 eruptions. Of course, that's somewhere on the globe of Venus, so you need to be in the right place at the right time, but still, it's not nothing, which is very exciting. And then you can kind of extrapolate this to a year, and you get to 42 eruptions on Venus per year. So quite something. But of course, this is scaling from the Earth to Venus, and we know that there's a lot of assumptions associated with that. It's not a perfect way of doing this. The method has a lot of drawbacks, let's say, and one of the drawbacks is that these 42 potential volcanic eruptions on Venus underestimate the amount of rift volcanism. So this is a breakdown of all the eruptions in the database of Earth that we use to scale to Venus, and you can see that there's about 750 eruptions in there, and most of them are associated with subduction zones, because those are the ones we see most on Earth. However, if you look at the actual lava that is being produced, most of it actually comes from rifts and oceanic ridges, so within the oceans like the Atlantic mid-oceanic ridge. And we don't have those eruptions in the database because they're in the ocean. We can't see them, which is obviously a problem. So that's why we can't take this into account in our analysis. So the 42 eruptions that we estimate for Venus is an underestimation and should be higher if we take into account the rift and mid-oceanic ridge volcanism that we see on Earth. Because obviously on Venus there are no oceans, so we don't have that problem as on Earth. On the other hand, it does overestimate the amount of subduction zone volcanism. We can assume, which is a big assumption, but still, we can assume that there might be some subduction on Venus. So subduction on Earth is where one plate dives below the other plate. And an example of a subduction zone is here the Aleutian Trench in the Pacific Ocean on Earth in this case. And Venus, we don't see these kinds of plate boundaries, but we do see corona. And this is the biggest corona that there is on Venus, Artemis corona. And as you can see, if you look at the topography, it kind of looks similar. So people have suggested maybe the coronae are like weird Venusian versions of subduction that we have on Earth. So you can assume that there is subduction on Venus, but again, you would overestimate the amount of subduction if you just scale, because on Earth you have about 50,000 kilometers of subduction trenches, whereas on Venus you only have about 10,000 kilometers of coronae rims. So if you take that into account, you lower the estimate, because the previous estimate was quite heavily biased towards subduction zones. and you lower it to about 12 eruptions on Venus per year, actively somewhere on the globe. But again, this underestimates the amount of rifts. So yeah, you can kind of make some, you can kind of attach some numbers to the amount of volcanic eruptions you could expect on Venus. And the next question is, what is the volcanic flux on Venus? How much lava is actually produced? And many people have thought about this before, and they've proposed basically everything, which, you know, makes sure you're probably right at some point. Just for reference, the volcanic flux, so the amount of lava that is produced at the surface of the Earth, is listed on the top. And you can see, okay, it's about 4 cubic kilometers per year, total extrusive volcanic flux on Earth, which means total amount of lava produced. If you look at Venus, like I said, everything has kind of been suggested, but people tend to think that it's a little bit less. So between 0.5 and 2 cubic kilometers per year on Venus. Interesting. If we know or think we know that that is the volcanic flux, can we then actually observe that with the new missions? Well, Venus Express in 2005 was capable of detecting an eruption if the volcanic flux was over 300 cubic kilometers per year, which you can see on the x-axis. Nobody even suggested that ridiculous of a number. So yeah, we couldn't do that. But Veritas, which will hopefully fly in 2028 or 2030, has about an 87% probability of detecting an eruption at a volcanic flux of 2 cubic kilometers per year. And we are kind of in that ballpark. That is what we kind of estimate for Venus at the moment. So that is very exciting. And then there are some synergies because, like I said, there's multiple missions going to Venus in the next decade. So if you combine the powers of Veritas and Envision together, you get up to 98% probability of detecting an eruption on Venus. So that's pretty good. That's very exciting. So we have a lot of cool things to look forward to if, of course, Venus is volcanically active. Then, if you assume that there's volcanism, well, with great volcanism, potentially comes great seismicity. Maybe. We're not sure. But on Earth, you know, volcanism is associated with earthquakes, and maybe we can have earthquakes, or rather venusquakes, on Venus as well. And how would that work? How many would we assume that there are then? Well, let's very briefly talk about tectonics for a bit. So this is a picture of the Earth with some plate boundaries that we see on Earth. And there are 3 types of plate boundaries. You have divergent plate boundaries where 2 plates move away from each other. And those can be rift zones or mid-oceanic ridges, depending on the type of crust that is moving away from each other. You can also have convergent plate boundaries where 2 plates go towards each other, and that can result in subduction, where you have 1 plate going below the other, or continental collision, where 2 plates collide and make a mountain, go up together, and you get mountain ranges. And then the 3rd type of plate boundary is transform plate boundaries, which you see at transform faults, and that's when 2 plates slide next to each other. Okay, that's the Earth. Great, cool. Plate tectonics, nice. But we know that there is no plate tectonics on Venus, really, because we don't see these very clear plate boundaries as we see on Earth. That doesn't mean that there is no tectonics, though. It's just not plate tectonics as we know it. There might be, you know, an infinite amount of ways we can have tectonics that we just don't understand yet. So maybe there is another form of tectonics, or some regional processes can be linked to it. And that is then where we can get seismicity from, because this movement of the plates with respect to each other, these are facilitated by earthquakes, where you have smaller regions displacing with respect to each other. Okay, so what are the tectonic settings on Venus? Well, there are more than this, but here I just show about 3 to give you an idea. This is a map of Venus, and in orange, kind of around the equator and the middle of the planet, you see a lot of rifts. Then there are these coronae, which are kind of round areas, which could be like subduction zones, kind of, in pink. So these are all these little dots. And then in purple, you have the ridges or the mountain belts where you have some convergent deformation, whether or not they're plate boundaries. So we have a lot of tectonic settings on Venus, and we can try to find Earth analogs and say, okay, we know how much seismicity we have on Earth for these kinds of regions. If we then apply that same amount of seismicity to the regions on Venus, we can kind of get an idea maybe how many quakes you would expect. So what we're going to do is we're going to look at the seismicity of Earth and scale it to Venus, kind of similar to what we did for the volcanoes before. So this is a map of the Earth now, and we divided it into different tectonic settings. So we have collisional regions, so for example, the Himalayas, and then we have subduction zones, etc. And we then take a catalog or database of seismicity, and we put that on top of this and sort all of the earthquakes in their respective tectonic region. And then we can calculate how many earthquakes there are in a given year, of which size for each different region. And then you get this. So here you can see on the x-axis the seismic moment or the moment magnitude. Those are the numbers at the top. And then the number of quakes per year bigger than or equal a certain magnitude. So the total amount of seismicity on Earth is this dotted line, the Earth seismicity reference line, and then the global amount of earthquakes that's actually been measured is in dark blue, which is mainly, it consists mainly of subduction seismicity, which is here in pink. And then you have all the other tectonic settings that have some kind of seismicity associated with it. Now, of course, there's very different areas associated with each tectonic setting. You have a lot of oceanic crust, for example. So even though you see quite some earthquakes associated with it, maybe the amount per square kilometer would be less. So we can kind of divide these lines by the area, and then you can see that, well, per square kilometer, you have a lot of subduction seismicity. You have a lot of earthquakes in subduction zones, and you have, moderate amounts in other tectonic settings. And if there is no plate boundary, there is not that much seismicity. So what we can then do is we take each of these and we apply the seismic density to the different regions on Venus. So first of all, we can assume that Venus is inactive, so no tectonics, no plate boundaries whatsoever. And then we say that that Venus has a seismicity like Earth's continental intraplate, so like in the middle of Russia, for example. And if we do that, this is kind of the range of seismicity you would expect on Venus, which is a few hundreds of quakes bigger than or equal magnitude 4. Interesting. Of course, I've tried to make the case that Venus actually is active. So if we assume that Venus is active, but we are a bit conservative in our estimates, we get this estimate. We get this by saying a selection of Venus's coronae are active and resemble subduction zone seismicity. Venus's ridges are similar to Earth's collision zones, and Venus's rifts are similar to Earth's continental rifts. And if you then add everything up, you get this range of seismicity on Venus, which is a few thousand quakes bigger than or equal to magnitude 4 on Venus per year. You can also be very liberal in your assumptions and take the most liberal assumptions. For example, that all of Venus's coronae are active, and then you get this estimate, which is quite a few thousand of quakes, magnitude 4 or larger. And if you plot these 3 estimates in one graph, this is what you see. So this is kind of the range of seismicity we could expect on Venus. The question then is, okay, how do you get active deformation under Venusian surface conditions? And for that, we're briefly going to look into some modeling studies, because people do a lot of modeling when it comes to Venus, so that's computer simulations. And one of the simulations that they do is rifting. So this is the model setup, and this is kind of Earth, and this is Venus. And it's basically a slice of Earth lithosphere or Venus lithosphere. And then you pull on both sides, which is what would happen in rift zones, where you have plates diverging from each other, so going away from each other. And you see what happens. And this has been done extensively on Earth. So we thought, can we do this on Venus as well? Well, the answer is yes. So first, let's have a look at the Earth model just to show you what this means. This is the accumulated strain, so the accumulation of deformation. And first, nothing happens. And then after a while, you see lots of things happening. The mantle goes up a bit here. And after 10 million years, you see this kind of brownish color is melt. The mantle has gone up. There's lots of deformation and colors happening. And you get, well, deformation and the plate boundary. Can we do this on Venus as well? Because we see these kinds of structures on the surface of Venus. So can we actually see it in a model? Well, let's have a look. Here we have the Earth model, just as a reference. And then if we add the pressure, the surface pressure of Venus to this model, this is the result after 10 million years, which, I mean, we're not going to play spot the difference, but it's not that different. Nothing much happens. Then if we add the gravity acceleration on Venus to the model, again, nothing much happens. And if you add both the pressure and the gravity acceleration, again, quite boring. It still all works, so great. But then, of course, the biggest difference between Venus and Earth is the temperature, the surface temperature of Venus. So if you add that, this happens, meaning nothing. So that's weird, isn't it? Because we see those structures on Venus, but if we just take our Earth model, where we know things work, and we apply that to Venus, nothing happens. So, you know, that means there is something wrong in our models. Some of our assumptions are incorrect. So this is how we can kind of learn about what is happening on Venus and how it works there. Because we need to find a way to get some deformation in this model as well, despite high temperatures. And one of the reasons, well, one of the things we tried was looking at the rheology. And the rheology is the way in which materials flow and behave and deform. And you can think about this as cooking spaghetti. If you have spaghetti and you haven't cooked it yet, you can break it very easily and it's very stiff, right? But if you cook it and you make it hot and you add a lot of water, then it becomes very pliable and it's more difficult to break. It likes to bend more. And that is rheology. And previously, we assumed Venus had the same rheology as the Earth, which is wet, a wet rock rheology, meaning that it's kind of like the cooked spaghetti. Clearly, that doesn't work. So we then tried, well, what if we have a dry rheology? You know, what if the spaghetti is uncooked? And then, if we do that, we add a dry rheology, we suddenly see that it's not a very boring picture anymore, but actually things are happening. And these are 3 different models where we have different ways of localizing the deformation. But things happen. So our models seem to indicate, you know, maybe Venus has a dry rheology. Maybe Venus in its interior is dry. We can also kind of compare with data very briefly, just to see if we are in the right ballpark on average. And we can see that well, the dotted lines are actual topographic profiles of 2 rifts on Venus. And on Venus, rifts are called chasma because that's cooler. And you can see that the bluish lines here, those are the lines with a 35-kilometer crustal thickness. They align more with the Ganis chasma, and the ones with the 25-kilometer thickness, they align more with the, in yellow, they align more with the Vana chasma. So maybe, very tentatively, these differences in topographic profiles that we observe on Venus could be due to differences in crustal thickness. All right, so I've showed you a lot now, and briefly going over what we've seen now, we've talked a bit about volcanism. Potentially, probably, Venus is volcanically active right now. And from scaling the Earth, you know, it can be about 12 to 42 volcanic eruptions on Venus in a year, using the data that we have available to us now. New missions could observe this volcanic activity, which is really exciting. So I invite you all to look forward to the data coming back in like 2030 or something. In terms of seismicity, it is also quite possible that Venus is potentially still quite active today, seismically. And it's probably less than or kind of similar to the seismicity of Earth, depending on your assumptions. In terms of tectonics and how things move in general on Venus on a regional scale, we found that a strong crustal rheology, so a very dry crustal rheology like your uncooked spaghetti, is needed to create rifts and deformation in our models. And we see that models with different crustal thicknesses of 25 to 35 kilometers are comparable to rift zones on Venus. So, you know, we're not that far off. Maybe our models are doing something right. And then there is a lot that I do not have time to talk about today, but is interesting nonetheless. So I invite you to ask questions or find me after this. One of those is plate tectonics. I mean, I've told you in between that probably it's not plate tectonics as we know it on Earth that is happening on Venus, but there is some kind of tectonics probably. And there are many different ideas, and people are trying to zone in on one particular idea of how it kind of globally moves, and the mantle convection and the tectonics. So we can talk about that later. And in terms of history, another great story that I haven't told you, but again, I would invite you to talk to me about, and I think there's also an exhibition piece in the library about this, is Guillaume Le Gentil, who had a very tragic life, but he dedicated his life to trying to study Venus. It wasn't always that successful. So that's a fun story if you want to know one. But for now, I'd like to conclude that Venus is very alive, very kicking, and in the future, there's a lot of potential for discoveries. So thank you very much for being here.
Wonderful talk. We are going to do Q&A if you guys have any questions. I have one that's from online really quickly as I put the charger in for our mic in the house. We know that Venus, or we think of Venus as a Earth's twin planet, but the question online is, how can Venus be Earth's twin planet because it's so hot? Temperature difference, or maybe they're curious to know, why do we consider Venus Earth's twin planet? Can you talk a little bit about that?
Yeah, that's a very good point. So Venus is usually called Earth's twin or Earth's sister planet, and that's because Venus has a radius that is slightly smaller than the Earth, so it's more or less the same size, and it also more or less has the same density. So of all of the kind of rocky planets that we have in the solar system, so that is Earth, Venus, Mercury, Mars, the Moon, which is a moon but also kind of a planet depending on who you talk to, Venus is the most similar to the Earth, based solely on its size and density. And those are, you know, kind of the two data points that are, those are the first two data points you usually get from a planet. So if we, you know, we can also talk about exoplanets. For exoplanets, those are usually the only things you know, the radius and the mass, and therefore the density of the planet. And for Venus and Earth, they're quite similar. So that's why they're called sister planets. But then people usually say, oh, it's Earth's evil twin because it's such a hot and hellish landscape, which I think is unfair. It's a really interesting planet. And yeah, the question is how, despite being so similar, are they so different? Is it just because it's closer to the sun? Probably not. Probably there's more to it. But yeah.
Can you give your...
Certainly. Oh, hi there. My name's Aaron. All the mysteries and the youth of the relative youth of some parts of the surface. The one thing you mentioned at the beginning was that it's actually upside down, or it's turning the wrong way. Isn't that indicative that maybe something happened to it? And could that not be something really key in all of our mysteries?
Yes, definitely. That's an excellent point. So people don't really know why Venus is upside down. One of the ideas is that there was some kind of moon or large entity, planetesimal, that collided with Venus, and therefore it started spinning the other way around. It got upside down. But beyond the fact that it's upside down, I'm not sure if there's a lot of evidence for that. Like, we have a similar theory for the Earth and the creation of the moon, where there was a Mars-sized planetesimal that collided with the Earth, and then you got the Earth and the moon. But obviously Venus doesn't have a moon. So beyond the fact that Venus spins weirdly, and this is not my expertise, I don't know if there is more evidence for that. But yeah, that could very much also, because that could potentially bring other kinds of materials to the planet and therefore change its whole evolution. So that could also be a solution to many of its mysteries.
Okay, we've got 3 in the room and 1 online. So I'm going to start at the back.
Oh, that's first.
I'm Nigel, a very interested observer of all things Venus since the late 70s to school. I'm just wondering, when I remember when they sent the Venera probe up in 78, I was reading about that time, the possibility of, they were discussing it a lot at NASA, this concept of terraforming to make Venus very much like Earth, to, you know, in case there was a problem with the Earth and we had to go to Venus. And it was a lot of talk, and it was supposed to happen 40, 50 years in the future, which is about now. So I don't know if you've heard about that concept, whatever happened to that. I remember it was in 1970 where they were discussing this in America in NASA, but it was one of those things that probably went the way of so many of these other programs. So then your thoughts are on this?
That's really cool. I didn't know that. Cool. Yeah. I mean, yeah, obviously that didn't happen. I think one of the main reasons is that Venus is, I mean, it's difficult to get around the hot surface, and it's also difficult to get around the large surface pressure and the atmosphere, which doesn't work. So the only thing I know, which is kind of science fiction-y, but you know, people like to think about, is that well, first, if there would be life on Venus, which is very, you know, at the moment, we don't have any evidence for that, it would be in the clouds. And then if Venus is ever habitable or could ever be habitable to humans, again, it would probably be in the clouds, because there you have, you know, reasonable temperatures and pressures. So you can think about, I don't know, aerial platforms where you just shouldn't walk off of or something. But yeah, that's probably very, very far in the future. I think people like Mars at the moment much more, because it's easier to warm things up than cool things down.
My question is, is just how Earth got hit by meteors, and the meteors were carrying water, and so the ice melted and turned it into water, covering Earth in water. Why didn't the same happen to Venus?
Oh my God, that's a good question.
Get its atmosphere.
Yes. Oh, well, if you can answer that, I think you're gonna win a lot of prizes. Uh, so yes, first thing, meteorites hitting the Earth. Well, I don't know much about meteorites hitting things, but what I do know is that Venus probably didn't get that many meteorites due to kind of gravity things, because before they get to Venus, they have passed Mars and Earth, so they can get grabbed by the gravitational field of those planets before they get to Venus. Then again, yes, if and we have evidence that there are meteorites that hit Venus because we see those craters, but maybe there was not a lot of water on Venus to begin with, whether it was in ice form or so it could turn into water or not. That's actually one of the big questions people are looking into, figuring out how much water there was on Venus and how much water there is on Venus. And, you know, if there was no water in the beginning, why not? And that kind of also relates to the atmosphere, because so people call them volatiles, so water and like really light elements that make up the atmosphere. The idea is they are in the beginning inside the planet, and then they need to get out and they form the atmosphere. But people don't know, actually people also don't really know about Earth, because it's all such a long time ago. It's very difficult to determine whether, like, if there were a lot of volatiles inside the planet, that could then make the atmosphere. So there's a lot of people that study the modeling of how the atmosphere formed, and many people have many different opinions. So we don't really know yet is the answer. But yeah, if anyone wants to study that or figure it out, again, probably a lot of prizes will go their way.
Well, the real curiosity that's driven all the missions to Mars is to discover if there's life. There's been some hints that there's phosphine in Venus atmosphere. And I'm wondering if that is driving any planned missions to Venus will try to understand if there are conditions there for some type of life.
Yeah, that's a good question as well. So there was, I think in 2021, people said, oh, we found phosphine on Venus and it can only have been made by life. So there is life on Venus, and everyone got really excited. And the timing of that press release and paper release was kind of very good, because it was early 2021 and both NASA and ESA had to make the final decision on whether or not to select Veritas and Envision, because there were two other non-Venus missions also in the running, and they had to choose which ones to do. And of course, from the Venus community, they were already for a very long time aware of the fact that people wanted to go back to Venus, but I don't think it hurt the panels that they saw that there was clearly a lot of interest in Venus with this story of phosphine. Having said that, they chose Veritas and Envision, which was great. I don't think it was mainly determined by the presence or not of phosphine, but since then, a lot of people have looked into this phosphine thing because it was so cool, and people reported about it, and they found, as far as I believe, that maybe there was not necessarily phosphine, or not as much. And if there was, people have since showed that there can also be non-life explanations for phosphine. So that kind of remains a mystery, although people are still obviously looking into it. And as for the missions, I don't think any current missions are really going there with the aim of finding life, but you never know what they find, and whether, I don't think phosphine is any of the main things they necessarily want to find, but I mean, they're not going to not look for it. So I think the fact that it broke at a timing story of around the selection was nice, and also to get Venus in the minds of everyone in the news and stuff, but probably wasn't a deciding factor.
I think you kind of answered the next question. We have several questions from our Zoom audience and from YouTube. One of them was any latest update on the phosphine on Venus. I think if you feel you've answered that, and go ahead and click done. The next question. So what do you think our plate tectonics here on Earth are so different from Venus? Do you have any ideas, or do they relate it back to the planet's formation?
Right. So coming back to the water question, which really is key to everything, that was a really good question, is that on Earth, plate tectonics probably is facilitated to a degree by water. So the water cycle is very, very important within the plate tectonic cycle, because it kind of lubricates things, and it makes, well, it changes the rheology. So you can get plate tectonics on Earth. And we think that on Earth, the fact that we have plate tectonics, the fact that we have water, the fact that we have life are all kind of interconnected. So by that logic, if you extrapolate that kind of badly, you would say, oh, well, on Venus, we don't see plate tectonics. So maybe that's because it has a different water cycle, or it has less water. Definitely at the surface, it has less water at the moment, but maybe it's trapped inside. So water could be a very big factor in terms of why the tectonics are quite different.
Okay, great. Another question, what are some arguments or other arguments that scientists may present or argue about about seismicity not existing on Venus?
Well, one of the things, if you want to have seismicity on Earth, things need to be able to break. So the rocks need to be able to break. So that's your pasta breaking, right? When it's uncooked. However, when things get hot, things get kind of gooey, and you can't break things anymore. Things flow or they bend. So the idea is, if it's very hot, then you don't get seismicity anymore, because things bend and they move in different ways. Of course, Venus is very hot. So the idea is that, well, Venus is too hot to have any seismicity. Could be, but I would argue, because that is what I study, that actually it can, I mean, it's much less the amount of the region where you could still break things, because it's much hotter, but there is still a region where you could have that.
Kind of a similar question, but to plate tectonics.
Yeah.
They asked the same thing. They have difficult imagining anything else but plate tectonics, because that's what we know on our planet for volcanism, I suppose. But are scientists thinking about any other reason for plate tectonics?
Yeah. So plate tectonics, as we know it on Earth, is yeah, you have one plate that goes below the other, or you have plates that move away from each other. But on Venus, other forms of tectonics or mantle convection regimes have been proposed. For example, you have the stagnant lid hypothesis, where you have just the crust that doesn't do anything. But in the mantle, you then have some kind of convection, and you get volcanism, but the surface isn't moving in and of itself. So that is, you know, a form of, well, a mantle convection regime, and I guess a kind of tectonics. Another one is that it's on a much smaller scale. So you have very small scale dripping, things that kind of break off at the bottom of the crust or the lithosphere and kind of go down. And then you have a lot of volcanism inside the crust, but it's not on a large scale where one plate goes below the other, but more small scale things. So those are, again, kind of tectonics, but not the plate tectonics that we know.
And I have a question from someone on Zoom who wants to talk to you. So I'm going to give it a try. I'm going to push the allow to talk button to see if they can unmute themselves and ask their question.
Hello there. So it was like a lovely webinar you hosted. My name is Maya Cutter, and I just wanted to ask you a question. regarding Venus, of course. So my question to you is that, like, since we understand that Venus is extremely hot in its atmosphere and its surface, now the question here is any technologies that we can use to improve Venus, because like Venus can somehow contain life, and if it does, then maybe we can use some technology to fix the its and bits which are on Venus, to colonize on Venus instead of Mars. So, like, Miss Iris, what are your views on that? And is there any technology that can be developed in the next 15 years? Thank you.
So if I understand the question correctly, it's about developing technologies that use Venus. What?
Think to help life, if life existed on,
Oh,
help it prosper. Is there anything?
right. Well, in the next 15 years, probably not. Things in space are very, very slow in general, because yeah, it just takes a really long time for people to get things going. There's a lot of money and et cetera involved. So within the next 15 years, probably not. In terms of developing something that could help with life, I think the most reasonable thing, but then you're talking probably about decades, if not decennia, is again these aerial platforms where it's, you can kind of be at a level in the clouds where it is more or less 25 degrees Celsius and nice. Because if you want to, yeah, it's very, very difficult to go to the surface of Venus and do something there. At the moment, there are some, because again, like most of the missions that I showed aren't landers. They are going to orbit Venus, except for Da Vinci, who's going to crash into Venus. But even Da Vinci isn't meant to survive on the surface of Venus. And the Russians had a lot of landers that they tried to get to Venus, and some of them crashed, some of them didn't. But they all lasted 2 hours at most. So getting things, like keeping them alive and not having them melt, is very difficult. Presently, there are some technology advances that, you can have a lander that will probably survive on Venus, that could have a seismometer for 3 months or something. So all the electronics would be fine. The two problems that you run into are power. How are you going to power it? You can't use solar power because there are clouds. So there's almost no sunlight that reaches the surface. So you would have to bring a battery, but then the battery also needs to be heat resistant. So that's very tricky. And the other one is the data stream, because you can do the measurements, but then how are you going to get that data to an orbiter and or to the Earth, which is again complicated. So those are kind of limiting factors.
Well, thank you so much, Dr. Van Zelst, for piquing our interest into Venus and continuing, our exploration of our solar system. Thank you so much for being here. I wanted to prompt you also to share some of your other things, if you want to, your YouTube channel or information. And don't forget, after this talk, we will head up to the library. If you'd like to join us, you are welcome to. And thank you to our YouTube and to our Zoom audience for joining us. So that's welcome. Thank you again, Dr. Van Zelst. Thank you.
Thank you very much.